Hey everyone, welcome to this explainer. Okay, today we are looking at something that is honestly going to completely flip how we see our place in the cosmos. We're heading high up into the Chilean Andes to explore how a revolutionary new observatory is about to film, well, literally the ultimate 10-year time-lapse movie of the universe.
All right, let's jump right in. I want to hit you with a massive number right off the bat, 3,200. That is the staggering megapixel count of the largest digital camera ever built for astronomy. And it sits right at the absolute heart of the Vera C. Rubin Observatory.
But this raises a pretty fascinating question, right? How exactly do you film a continuous, dynamic movie of the entire southern sky? Because before this, astronomers usually just stared really deeply at tiny little patches of space. To capture the whole sky dynamically, that takes an absolute engineering miracle. We're talking a combo of unprecedented hardware and software, which we're going to unpack right now. Just to give you a sense of the sheer ridiculous scale we're dealing with here, take a look at the scientist standing next to the camera's internal lens. It is 1.57 meters wide. That's actually the largest internal lens ever manufactured for astronomy. It really gives you a feel for the monumental engineering required just to focus the starlight. And to put the whole camera into perspective, just picture a minivan in your head. Now imagine that minivan weighs 2,800 kilograms and is absolutely packed with a sensor array made of 189 highly sensitive CCDs. That's essentially the digital film of the camera, and it has to be cooled to minus 100 degrees Celsius. The resolution is so insane that if you wanted to display just one single image at full size, you'd literally need 400 Ultra HD TVs lined up.
So feeding light into a camera that massive requires a totally revolutionary mirror design. Instead of using separate primary and tertiary mirrors, the engineers over at the University of Arizona actually fabricated both curves out of a single monolithic slab of glass. And by combining those two mirrors into one, the massive Simone Survey telescope becomes incredibly compact and super stiff. And that is absolutely crucial, because it isn't just staring at one spot. It has to be fast. It literally needs to physically dart across the sky and settle down quickly without vibrating, all so it can take these rapid-fire images.
Shooting the cosmic movie, the LSST. Let's look at how all this revolutionary hardware builds the foundation for the core mission.
You see, the LSST represents a total paradigm shift. Traditional astronomy usually involves staring deeply into one tiny patch of the sky, kind of just hoping you get lucky and catch something interesting. But Rubin's strategy is what scientists call wide, fast, deep. It rapidly scans the entire southern sky in these massive, panoramic, time-sensitive sweeps.
Thanks to that massive camera and mirror we just talked about, every single exposure covers an area of the sky 40 times larger than the full moon. Seriously, 40 times! By doing this continuously, the observatory is going to completely map the visible southern sky every 3 to 4 nights, and it's just going to repeat this cycle for an astonishing 10 years.
Real-time astronomy, the alert pipeline. Because honestly, capturing these images is really only half the battle. We're entering the era of whoosh, flash, bang astronomy.
This data pipeline is just blistering fast. Imagine this. An image is captured in Chile. It immediately hops onto a 16,000-mile-long Hall network managed by Florida International University. It travels under the ocean, and it hits a supercomputer in California in seconds. Once there, it's instantly compared to older images. If anything is changed, moved, or exploded, a public alert is issued within 2 minutes of the shutter closing. 2 minutes!
So the absolutely crucial point here is this number, 7 million. When the observatory reaches full operations, it's going to issue up to 7 million of these real-time alerts every single night. That is an absolute tsunami of astronomical data, and it's going to be available not just to professional astronomers, but to citizen scientists all over the globe.
But what exactly is triggering millions of alerts, right? Well, basically anything that moves or flashes. We're talking supernova explosions, hazardous near-Earth asteroids streaking by, variable stars dimming, or even flickering supermassive black holes waking up to feast on some matter. It completely shifts astronomy from a static science to a highly dynamic one.
This highly dynamic approach is going to help us solve some major mysteries. Take supermassive black holes in the very early universe, for example. The astronomer Eduardo Bañados actually said that finding these massive objects so early in cosmic history is, quote, like discovering a full-grown adult in a kindergarten class. It's wild.
Rubin's cosmic movie is going to track how these black holes flicker over time, which will hopefully help us understand how they manage to grow so inexplicably fast.
Okay, let's just take a breath here and zoom out for a second. Beyond the fast-paced alerts and all those roaring data pipelines, the ultimate goal of the Rubin Observatory is deeply, deeply profound. It's actually looking to solve the mysteries of the invisible universe. Solving the dark universe, honoring Vera C. Rubin. This brings us to our final act, mapping the invisible forces of the cosmos and the incredible legacy of the woman this flagship observatory is named after.
You know, for decades, women in physics faced immense structural barriers. As the quantum physicist Dr. Shohini Ghose noted about her own education, she said, "I really didn't know of any woman physicist apart from Marie Curie." So naming this groundbreaking observatory after the brilliant American astronomer Vera C. Rubin is a really vital step in correcting that historical invisibility.
And Vera C. Rubin's work is exactly what this telescope is built to investigate. Back in the 1960s and 70s, Rubin mapped the rotation of spiral galaxies and proved that they were spinning way too fast to be held together just by the stars we can see. She basically provided the fundamental evidence for the existence of dark matter. That's the invisible material we now know makes up about 85% of all the mass in the universe.
But how do you film something invisible? Well, the observatory is going to use a technique called weak gravitational lensing. Here's how it works. As light from billions of distant galaxies travels toward Earth, the gravity from that invisible dark matter web actually bends and distorts the light just a tiny bit. By precisely measuring those minute distortions across the entire sky, Rubin is finally going to map the invisible scaffolding of our universe.
By generating a whopping 20 terabytes of data every single night, the Vera C. Rubin Observatory is about to capture a universe that is far more active, more crowded, and way more mysterious than we ever imagined. So when this 10-year cosmic movie finally reveals the invisible forces shaping our cosmos, how will it rewrite our very understanding of reality? It's a pretty thrilling question, isn't it? And the cameras are about to start rolling. Thanks so much for joining me for this explainer today. And hey, keep looking up.